Okay. Now, you remember in the previous class we had developed the flow, both flow and velocity as well as the shear stress profile. Now, we also said that in cases we will do some problems, and the moment you do some problems, that will give you some confidence that yes, I can solve some of the problems, right. So, that if we can see, this we also said that viscosity we had developed, we had determined theoretically, of course, in some cases that was through capillary in earlier class, right. Now, another way of finding out viscosity is that you have seen that Brookfield viscometer, right, and that in the very earlier classes you have seen that we said that one fixed container and one rotating container, inner container was fixed and outer container was rotating, and by that way the viscosity can be determined, right. And we found some expressions for that shear stress also, okay, as well as the velocity profile. And in that case we said that yes, you can develop the theoretical relations for finding out the viscosity, and same is used for Brookfield, or we also showed through capillary tube, right. Now, another one we would like to also highlight or establish, that is when you have a small tube through which a ball is dropped, and if the ball is dropped, then depending on the viscosity of the fluid through which it is flowing, through which the ball is dropping, it will take the time. So, if you know the time required from one height to another height, how much it is taking time, then from there also you can determine the viscosity. This is another way of determining the viscosity, right. So, let us do one such problem by which we can determine the viscosity theoretically. This is of course based on definitely on the buoyancy forces acting on it, and the relation is also known in most of the cases, but still we have to find out. Let us do that. The problem is like this: a sphere is allowed to fall from rest, that is when it is not moving, it is at rest, is fall from a rest in a viscous fluid. The rate of all the sphere, the rate of fall of the sphere in the fluid can be measured at steady state. Derive a relation to get the viscosity of the fluid. I repeat, a sphere is allowed to fall from rest in a viscous fluid. The rate of fall of the sphere in the fluid can be measured at steady state. Derive a relation to get the viscosity of the fluid, right. So, obviously, the sphere when it is falling, it will accelerate until it reaches a constant velocity, which is known as the terminal velocity, right. So, at this state, when the terminal velocity is attained, sum of the forces acting on the sphere must be equal to the sum of the forces when you acting on this sphere is equals to 0, because that time it attained the terminal velocity, right. And these forces are force of gravity on the solid ball acting in the direction of the fall, and the buoyancy force and the force due to flow of the motion of the ball acting in the opposite direction. So, these two forces, when you are countering, when you are accounting for, then that will give a relationship. From there you can determine the viscosity, right. So, let us look into the sphere will accelerate until it reaches a constant terminal velocity. At this state, the sum of all the forces acting on the sphere must be 0. And now, the force of gravity on the solid ball acts in the direction of the fall, and the buoyancy force and the force due to fluid motion act on the opposite direction, right. So, this we can say then the volume of the sphere is 4/3 pi r cube, right, and density of this sphere, if it is rho s sphere and the gravity is that. So, this is 4/3 pi r cube rho s into g, which is the gravity force acting on the ball, and the buoyancy force which is acting on the ball is also the volume of the sphere 4/3 pi r cube into the density of the liquid rho into g plus the 6 pi mu v terminal velocity into r. So, the we said the gravity force and the sum of the forces acting on it is equals to 0. So, if you take all of them in one side, then it becomes this minus this equal to 0, right. So, here that rho s is the density of the solid, and this rho is the density of the liquid, or said rho L if we write in a better way. So, this is the density of the liquid, right, and V t is the terminal velocity. Right, rho L is the density of the liquid, then rho s is the density of the sphere solid, right, and r is the radius of the solid sphere, right, and g is the acceleration due to gravity that we know, right, and mu is the viscosity of the liquid. Right. So, if this be true, then from this relation we can write that mu is equals to 2 r square into rho s minus rho liquid over into g over 9 v terminal, right. So, this mu is equals to 2 r square rho s minus rho liquid into g over 9 v terminal, right. I hope you have seen this when you have done Stoke's law, right. So, this is nothing but Stoke's law, and from there if we know the terminal velocity, if we know the density of the liquid, if we know density of the solid, if we know the diameter of the sphere, then we can find out the viscosity of the liquid, right. So, this mu is rather mu L, that should be said. Of course, solid that does not have any viscosity. So, this is again valid when RE or NRE Reynolds number is dV terminal rho of the liquid by mu is less than 0.1. This is valid when the Reynolds number is less than 0.1, defined as dV terminal rho of the liquid by mu of the liquid. So, if it is less than 0.1, then we can determine that viscosity, right. So, let us, can we do one, just frame out one problem and do it. For that, you remember earlier we had given diameter of this, say, solid is 1.7 into 10 to the minus 3 meter, right, and rho of this solid, depending on that the viscosity will be of course determined, we are taking arbitrarily. So, rho of this solid, that if we take to be equal to, say, around 50 or 5000 kg per meter cube, arbitrarily of course I am assuming. Rho of the liquid, say water, 1000 kg per meter cube. This density might be too low, however, rho of the liquid is that, and G we know to be 9.81, right. Then the viscosity, that can be written as mu liquid, this is 2 into 1.7 10 to the power minus 3, right, whole square divided by 2, right, into this is 5000 minus 1000 into G is 9.81, right, and terminal velocity, let us assume to be, say, this is 9 into, as we have seen earlier, say it is 0.03 meter per second. Then if we look at this, the value, find out the value, and then that will give you the viscosity of the liquid, right. So, this way we can find out the viscosity of the liquid, and obviously this is an application of the Stoke's law, which we know, right. Now, let us go into another situation, a fresh situation, where we can have, you know that for homogenization, that you get milk every now and then. So, that milk is normally homogenized. No? So, for homogenization, what is done, you know, high pressure liquid is, or milk is passed through a very small orifice. That orifice determines what will be the diameter of the fat globule. Now, first of all, homogenization means that you are homogenizing fat particles. In milk, if you take, you might have seen that the fat particles comes out and floats on the surface with time. You buy from the market not the homogenized milk, normal uh, normal wherever is available fresh milk if you buy, and then keep it just like that for couple of hours. You will see that fat particles are coming up on the surface, and because their sizes are big, and this from this what Stoke's law we have seen, there also you can find out what is the time required for the fat particles to come up, right? The same thing. Okay. So let us look into that. Then perhaps the next thing will be much more easier to visualize, right? But before that, let me tell the situation what happens. We'll do again one problem. Here also only we'll constitute that problem. We'll frame out the problem and solve it with the help of that Stoke's law, which we have just defined, right? And say now what is happening in homogenization, that a high pressure, say this is a slit through which a high pressure liquid is coming, right? Here that milk is coming and going through, this is the enlarged view. This size could be 2 micron or 3 micron or 4 micron or 1 micron, depending on what you need at the exit of the homogenizer. If this is the homogenizer, right, this is the point where through which homogenization is taking place, called homogenizing valve, right? This is called homogenizing valve. So this is another application. Unless we know the applications what you are using, because then it becomes only mathematics and little physics, not engineering. So unless we know where you are applying, for what you are developing, so no, I think the concept becomes not clear, or the applications are not known. So that is why in every stage I am trying to give some or other application where you can apply the things which we are being teaching, right. So when you are doing this, that at this high pressure, through when it is coming to this molecules, rather the fat globules, this is called not called molecules, these fat globules of different size, maybe say this is say 20 micron, say this is say maybe 30 micron, say this is 10 micron, they do go together and come out of this slit, right. This slit diameter we assume to be say 2 micron, right. So in that case, when it is going through, then what happens, there are both normal and shear force act on that, and the molecule, this fat globule that appears like this, right, and the forces acting on that, then that disintegrates it into, depending on the size, if it is 20 micron, so 10 such things will be coming, and each will be around say 2 micron in size. So you will get membrane, or sorry, a fat molecule like this, which will come out from here of 2 micron. So this is the application which we will do in the, if possible, in the start with this class, or maybe we will be doing in the next class depending on the time available, right. So I hope is very to go into this. Before that, let us also find out that the previously we had done that Stoke's law, that equation, if you remember, that was mu, right, that was mu liquid is equals to 2r square then rho S minus rho liquid, right, into G divided by 9 V T, right. V terminal then becomes equals to 18, right, R square into rho. In this case, this will be which one is higher, rho liquid, rho this, right, rho S minus rho liquid into G by mu liquid, right. So, this is that one which you know by the Stokes law. 9 and 2 becomes no. So, this is not 18. So, V T will be mu L comes down, right, and V T goes there. So, this is 2 by 9. So, not 18, 2 by 9, right, and this is d square, right. So, that is 2 to 4. R is equals to d by 2, right, d square by 4, right. So, that means this becomes d to the power d square rho, in this case let us write fat, minus rho liquid into G over this goes out. So, 18 mu L, right. So, now if we say that how much time it will take or at what velocity this fat molecules or fat globules will come to the surface, right, at what level. This is going through the milk, right. So, milk has a density, so then it has also a viscosity, and if this is the surface of the container, if this is the container, if it is the surface of the container, so at what velocity these fat globules will move, we take the average fat diameter to be some value, say 5 micron, 6 micron average, right. So, 6 micron average we take, and at what velocity this will come to the surface, right. If we can find out this one, then this will give us some idea that why we need to go for homogenization of the milk, right. Then we will go how the velocity profile etc. is occurring into this, right. So, here we said that average size of the fat globule is 6 micron, density of liquid, then d fat is equals to 6 micron, density of liquid is liquid in this case milk, rho fat is equals to say 900 kg per meter cube, and density of milk is say 1030 kg per meter cube, right. And another thing is required, mu milk, right, is say earlier we had seen around it should be around say 1.5 10 to the power minus 3 Pascal second, right. In this case, then the terminal velocity that should be d is 6 micron, 6 into 10 to the power minus 6 square, right, into rho fat minus rho liquid, we take delta L. This delta L means higher minus lower. If rho fat is density is low, then rho liquid, then it will go up, and in case of if it is solid, right, like the same thing is applicable to another situation, like where you have a container and you have some mud, right. This mud is there, and if you allow it to keep for some time, it settles down. That's called settling, right. That settles down are called settling. There also similar, this mud or solids, they do settle down, and the rate at which it is settling is also can be predicted or can be determined with the help of this equation, right. And there you find out the terminal velocity at which it is dropping, and then coming to the bottom layer, right. So, here there the density of the solid is higher than the density of the liquid. In this case, density of the liquid fat is lighter than that of the milk. So, that is why fat globules will go up, and here this will go down. So, that is why delta L is taken. So, depending on if the terminal velocity becomes negative, that means it is going up. Velocity cannot be negative. So, it is going up, and if it is positive, that means it is going down, right. So, 6 10 to the minus 6 in this case, if we take the delta or the mod value, then it becomes 1030 minus 900. That means you have 900, 100, 130. So, the difference is 130, and G is 9.81, and this 18 into 1.5 10 to the power minus 3. So, this becomes equal to, let us look into calculator. That 6 into a minus 6 into, or 6 square rather, right, into 130, right, into 9.81, right, divided by 130, right, so much. What did I do? It is 6 square into 130 into 9.81 is equal to so much divided by 18 divided by 1.5 right, divided by 10 to the 6 and 3 9. Ten to the 6 9, that is 10 to the power 9, 10 to the power 9 is equals to 0.000 0.000017 meter per second, right. It is so low, that is 1.7 into 10 to the power 1.7, 1, 2, 3, 4, 5, 6, 10 to the power minus 6 meter per second, right. So, if we take in terms of meter per hour, then it will be 3600 into 3600. So, that means it will be 0.006 meter per hour, 0.006 meter per hour. That means if we take again meter, that means if we take 100 or 1000, the 6 millimeter per hour is the velocity, 6 millimeter per hour that will travel if through this. So, you see 6 millimeter means roughly this. So, this distance it will take around 6 millimeter. That is why you need to keep it for some time, so that the fat globules are coming out, right. So, this is what is required, otherwise you will not be able to find out the meaning or the requirement for your developing this kind of relations, right. So, this we have done, okay. Here this was, if you would have taken this instead of 130 positive, it would have been negative. So, that would have been a negative value of Vt, but velocity cannot be negative. So, that is why the negative sign would have implied that it is going towards the upper direction, right. And if it would have been towards the bottom side, that is, if it would have done with the help of the denser particles, then that would have come to the bottom of the container, and then this 130 would have been positive, right, and velocity indirectly would have come to the positive value, right. So, this implies that why we need to know that how the homogenization is required, or what is the usefulness of the thing which we are going to develop, or which next we will be doing, right. That will be flow through the small orifice, or flow through the small flat plate between two fat plates which are very fine apart, right. So, there similar kind of things will happen, okay. So, we will do in the next class. Thank you.